Hello everyone. Today we are going to discuss about field theory. First of all, what is meant by field? A field is a non-empty set together with two binary operation, let us say plus and multiplication dot. It is denoted by plus and dot, satisfying the following conditions. What are they? Your set, say F, together with addition should be abelian group. So it has to be a abelian group under addition. And the second condition is the set of all non-zero elements should be abelian group under multiplication. And distributive law holds. If all these conditions are satisfied, then we say F is a field with the binary operation addition and multiplication, plus and dot. It need not be a general addition and multiplication. They are denoted by that symbol. So, first of all, let us define what is meant by characteristic of a field. And we'll see certain results on characteristic of a field. What is meant by characteristic of a field, F? It is the least positive integer, say n, such that n into multiplicative identity of the field should give you 0. You can write this one also like this. Instead of writing n times 1, we can write this one as 1 plus 1 plus 1 n times. So sum of 1's n times should give you 0, or n into 1 should give you 0. Both are one and the same. And in general, there need not exist such positive integer. In that case, the characteristic of that field is said to be 0. For example, in the case of rationals, the set of rationals, we knew that set of rationals is a field. It's impossible to find a rational number for which the product of that rational and 1 gives you 0. Therefore, the characteristic of a rational number set is 0. If you take another example, say for example Z2, the collection of all residue class of 0 and 1. We knew that it forms field with respect to the binary operation addition modulo 2 and multiplication modulo 2. And there is a positive integer 2 which gives you 2 into 1 is equal to 2, but under modulo 2 it becomes 0. Therefore, characteristic of Z2 is 2. So, characteristic may be 0 or characteristic may be a finite value. So, let's prove in general proposition. Characteristic of any field is 0 or a prime number. And further, if characteristic of a field is 0, then n into a is equal to 0 implies either n equal to 0 or a equal to 0. And if characteristic of a field is a prime number, then p into a will be equal to 0 for all a belongs to F. Let us prove this first. And using this, we can prove this very easily. Suppose characteristic of a field is 0, there is nothing to prove. That is what needed for us. So let's assume that characteristic of a field is non-zero. Let us say characteristic of a field is some n, which is non-zero. Then we have to show that n is a prime number. Because characteristic of a field is either 0 or a prime number. Since we said characteristic is not 0, we have to show that then that number is a prime number. So we have to show that n is a prime number. But let's assume a contradiction, that n is not a prime number. Then n is a composite number. Then a composite number can be written as product of two numbers, say m1 and m2. Because our n is positive integer, product of these two must be positive. And let's say both are positive number, and we knew that your m1 is less than n and m2 is also less than n. And since n is the characteristic of the field, n into 1 should give you 0. But what is over n? N can be written as m1 into m2 into 1 equal to 0. But this can be written as m1 into 1 and m2 into 1. Their product equal to 0. And you should note that your m1 into m2 I mean m1 into 1f and m2 into 1f is giving you 0. And your m1 and m2 are positive integers. And your z is an integral domain. And in the integral domain, product of two numbers will be equal to 0 only if at least one of them is 0. Then only this is true. So either m1 into 1 is equal to 0 or m2 into 1 is equal to 0, because m1 and m2 are positive integers and z is an integral domain. For the time being, let us assume that, without loss of generality, that m1 into 1 is equal to 0. But if m1 into 1 is equal to 0, then since m1 is less than n and m1 into 1 is equal to 0, therefore m1 is the least positive integer for which this is equal to 0. Therefore characteristic of f is m1, which is a contradiction, because characteristic of f is n, and no number less than n gives you product of that number into 1 equal to 0. Therefore this is not possible. Then if you take this, so if this is not possible, then we are obviously this has to be true. But if this is true, then again m2 is less than n and there is a number m2 with which 1 is product of 1 is giving you 0. Then m2 is a characteristic of field f, which is a contradiction. Thus none of these two are true, hence our assumption is wrong that n is a prime number. Therefore n is not a prime number is false, hence n is a prime number. Thus we have proved characteristic of any field is either 0 or a prime number. And let's prove this result first. After this we have to show this. Let us assume that characteristic of a field is P. Then we have to show that P into A equal to 0. But P into A is nothing but A can be written as sum of A, P into A can be written as sum of A P times. That is one and the same as P into A. But A can be written as A into 1, because your F is a field and identity law holds in F. So A into 1 is simply A. If you write this again by distributive law, I can write this one as A into 1 plus 1 plus 1. But how many 1s are there? P times 1s are there. So I can write this one as P times 1. But since characteristic of a field is P, we knew that P into 1 should give you 0. So this will be 0. 0 into anything is 0. Therefore we have proved P into A equal to 0. And so if P into A equal to 0, because you know that if P into A equal to 0, then either P equal to 0 or A equal to 0. Why? If characteristic of a field is 0, then since your n into A is giving you 0, so 0 into A will be equal to 0, or if A is 0, then it is 0. Because of that fact, this is trivially true. Hence, this completes the proof. Now let's see the remark. The characteristic of a field is the additive order of the multiplicative identity of the additive group F of the field F over the binary operation addition. Why? Because, see, what is your multiplicative identity? It is 1. What is meant by order of an element? In the case of group, order of an element is the least positive integer, say n, of an element A, if A to the power of n equal to identity element of that group. So A to the power of n equal to E, then and if n is the least positive integer, then n is the order of A. That is what the definition of order of an element in the group. Now, Here we are considering multiplicative identity. Therefore, 1 to the power of n should be equal to identity element. But what is your group? It is additive group. So what is additive identity? 0. So 1 to the power of n should give you 0. 1 to the power of n should give you 0 means, and n is the least positive integer. So 1 to the power of n can be written as, under the binary operation addition, 1 plus 1 plus 1 n times. That is one and the same as saying n into 1 is equal to 0. But we knew that n is the least positive integer and n into 1 is equal to 0 means it is nothing but characteristic of that field. So characteristic of the field is the additive order of the multiplicative identity of the additive group f of the field f. Now if f is subset of k, then we knew that in the case of fields, both additive and multiplicative identities are same. And if one is the multiplicative identity of the field f, then one is also multiplicative identity of k. And if the characteristic of a field is say n, then n into 1 will give you 0. The same one you are considering in k, therefore the same one should satisfy the condition n into 1 in k should also give you 0. Therefore, the characteristic of field f and characteristic of field k are one and the same. And if suppose f and k are two fields such that f is contained in k, then f is called as subfield of k, or we can say k is the extension field of f. And further, the smallest subfield of k is called as prime subfield of k. So, what is the smallest subfield? The name for smallest subfield of any field, it is called the prime subfield of field k. Let us consider collection of all subfields of k. And we knew that intersection of any two subfield is again a subfield. So, intersection of this collection, which contains the common elements of f alpha, is contained in all f alphas. Therefore, this subfield is the least among all the subfields of f alpha, because you know this integral alpha f alpha is subset of f alpha, and f alphas are the subfields of k, and among them this is the least. Therefore, this itself is called as prime subfield of k. So intersection of all the subfields, collection of all subfields of k, is the prime subfield of k. Now let's move on to a theorem. What is that theorem? The theorem says the prime subfield of a field is isomorphic to either rational number set or the residue class of integers modulo p, depending on characteristic of a field, whether it is 0 or a prime number p. So let's prove this one. We have to show that the prime subfield of this k is isomorphic to q or zp, depending on the choice of characteristic. Now let us consider set R, which is product of n into 1, where n is the integer. Now obviously this is collection of all elements which satisfies the integral domain conditions with respect to these two binary operations. And in fact, you should note that this collection is the subring of the field k. Now define a ring homomorphism phi from Z to R. Remember, your Z is also integral domain and R is also integral domain, by phi of n is equal to n into 1k. Remember, this n is coming from Z only, but your n into 1k belongs to R. and same n is present in Z. Then this phi is a ring homomorphism. Why? Because image of m plus n under the mapping phi is equal to, by this definition, we can write this one as m plus n into 1. Since your m plus n into 1 can be written as m into 1 plus n into 1 by distributive property, this is nothing but phi of m and this is nothing but phi of n. Therefore, we have proved phi of m plus n is phi of m plus phi of n. And further, the image of mn under the mapping phi is, by this definition, if it is mn into 1. But by associative property, this can be written as m into 1 into n into 1. But what is your m into 1? It is phi of m into phi of n. And clearly these two conditions are satisfied. Therefore, phi is a ring homomorphism. And further, remember your n, the same n is considered here. Therefore, this inverse image of n into 1k is n. Therefore, phi is onto. Thus, we have proved that this phi is onto ring homomorphism. Hence, I can apply fundamental theorem of homomorphism of rings. What do your fundamental theorem of homomorphism of rings says? Domain divided by kernel is isomorphic to codomain. So, your R will be isomorphic to Z by kernel. Domain divided by kernel is isomorphic to codomain. Now, what is your R? Your R is an integral domain. Hence, this is also an integral domain. Now, we are having a result. If R is a ring and if P is an ideal of R, then the ideal P is a prime ideal if and only if R by P is an integral domain. By that result, since this is an integral domain, this kernel phi is a prime ideal of Z. But we knew that the prime ideals of Z are ideal generated by 0 or ideal generated by a prime number. We have proved that result in the earlier classes. So, kernel phi has to be either ideal generated by 0 or ideal generated by P. We are having two cases. Now let's consider the kernel is generated by 0. Then R is isomorphic to Z by ideal generated by 0, which is nothing but isomorphic to Z. So your R is isomorphic to Z. In fact, we need a prime subfield of K. Now, your R is an integral domain and Z is also, we know that it is an integral domain. So, we need a smallest field containing this integral domain R. So, the smallest field containing Z is nothing but its field of quotients. And what is the field of quotient of Z? It is Q. So, the prime subfield of K is the smallest field containing R. And so, it must be the field of quotients of R. Thus, the prime subfield of K is isomorphic to the field of quotients of R, which is isomorphic to the field of quotients of Z. That is Q. Now, we knew that kernel phi is 0. So, what is the definition of kernel? It is collection of all domain elements for which phi of n will be equal to 0. But what is your phi of n? N into 1. N into 1 equal to 0 means what? N into 1 is equal to 0 implies n equal to 0. Because if n is non-zero, then n into 1 can never be 0. Therefore, n is 0. That means characteristic of this field is 0. So characteristic of this field is 0 and the prime subfield is isomorphic to Q. Now let's move on to the second case. So we approved the kernel, the characteristic is 0, then the prime subfield of K is isomorphic to Q. Now let's move on to second case. What it says, suppose kernel phi is generated by the ideal generated by P, where P is a prime number. Then R, which is isomorphic to this, is nothing but Z by ideal generated by P, but this is nothing but ZP. And we knew that ZP itself is a field, so that means R itself is the field. Therefore, the prime subfield of K is R itself, but that is isomorphic to ZP. What is the meaning of kernel phi is ideal generated by P? We knew that kernel phi contains collection of all those domain elements for which phi of n is equal to 0. And you are saying this is the ideal generated by P, that is Pz. Both are one and the same. That means P is the integer which gives you P into 1 equal to 0. So P is the smallest positive integer such that P into 1 equal to 0, which implies that characteristic of K is P. So when characteristic of K is P, the prime subfield of K is isomorphic to ZP, and this completes the proof of this theorem. Now let's see the remark. Remember here, whenever we write 1K, 1F, that means they are multiplicative identity of field F, just to indicate that it is a multiplicative identity of that field. Otherwise, simply you can write 1, no distinction between them. And if characteristic of a field is P, then you don't have to write P into 1K or P into 1. Simply you can write P equal to 0. And the fields of characteristic of P are finite fields, or fields of finite characteristic. And those fields whose characteristic is 0 must be infinite, because the smallest field itself is isomorphic to Q. Therefore, such field must be the infinite field. And suppose characteristic of a field is prime number, then the field may not be infinite or finite. It depends. It may be finite or it may be infinite. For example, let's consider K, which is a field. Actually, this should be simple bracket. That indicates that the quotient polynomials defined over Z2. It is not square bracket, it is simple bracket, because your K is a field and this is not a field. Let us consider K is a field generated, which is collection of all quotient polynomials defined over Z2. Then your Z2 is subset of this. This is not field, but it is an integral domain. This is subset, not equal. Subset of Z2 of X, which is a quotient polynomial, and this is a field. Note that your Z2 is finite, but this field, this is smallest field, prime subfield. But this is not finite. Why? Because this itself is not finite. It contains 1, x, x square, x cube, etc. Therefore, this is also infinite. So it depends on the choice. It might be finite or it may not be finite. I'll stop at this stage. Thank you.